In this video, I will derive an expression for the terminal voltage of a cell. Now, in a circuit, there could be two kinds of cells, one driving the current, one opposing the current. Now, the terminal voltage expression for the one which is driving the current will be different from the terminal voltage expression of the one which is opposing the current. Now, this cell has EMF epsilon 1 and internal resistance R1. This cell has EMF epsilon 2 and internal resistance R2. So, this cell is driving the current in this sense with a force of epsilon 1, and this cell is opposing the flow with an EMF epsilon 2 in this sense. So, this cell is pushing current in this sense with epsilon 1, and this cell is pushing the current in this sense with epsilon 2. So, the net EMF in the clockwise sense is going to be epsilon 1 minus epsilon 2, as epsilon 1 is greater than epsilon 2. So, net EMF equal to epsilon 1 minus epsilon 2, and that is equal to I times the net resistance. Now, this circuit has three resistors, one is R1, one is R2 and one is capital R. All three are in series. So, I times R1 plus R2 plus capital R. Now, this is equal to I times R1 plus I times R2 plus I times capital R. Now, if we subtract I times R1 from both sides and add epsilon 2 to both sides, then we get IR1 and IR1 getting cancelled. So, here we have epsilon 1 minus IR1, then epsilon 2 getting cancelled is equal to epsilon 2 plus IR2 plus I capital R. Now, this is the terminal voltage across the cell number 1. So, this is V1 and this is V1. So, this is the terminal voltage across cell number 1, and cell number 1 is driving the current, and this is the terminal voltage across cell number 2, and cell number 2 is opposing the current, and the voltage is V2, and this is the potential drop across the resistor capital R. So, we can clearly see the terminal voltage of the cell driving the current is epsilon 1 minus IR1, and that opposing the current is epsilon 2 plus IR2. Thanks for watching.